For almost the entire story of our species, gravity was invisible. Not invisible in the literal sense. We saw its effects every day. Apples fall, rivers flow downhill, planets trace patient arcs across the night sky. Yet no one had a name for the mysterious pull that guided everything. In early civilizations, falling stones and marching stars belonged to different realms. The heavens were perfect and divine. Earth was messy and temporary. The idea that both were ruled by the same law would have sounded absurd. In ancient Greece, the philosopher Aristotle tried to explain motion by imagining a universe full of purpose. Every object, he said, had a natural place. Fire climbed upward because it belonged to the heavens. Stones fell downward because they belonged to the earth. Nothing attracted the stone. The stone simply wanted to be home. To us, this feels poetic, but not scientific. Yet for nearly 2,000 years, this idea shaped how scholars thought about motion. No one questioned it, because no one had the tools to measure it. Then, in the early part of the 1600 years, an Italian thinker changed everything. Galileo Galilei did not trust authority. He trusted experiments. He rolled spheres down inclined planes and measured how far they traveled in equal slices of time. If an object had a natural place, it should behave differently depending on what it was made of. But Galileo found that everything fell in the same way. A feather and a stone would accelerate at the same rate in a vacuum. Gravity did not care about purpose or natural order. It simply acted. Still, the question remained. Why does it act at all? The answer arrived with a curious young man in England. When the plague forced him away from university, Isaac Newton retreated to the countryside. In those quiet years, he developed 3 laws of motion and a startling new idea. The same pull that brought an apple to the ground was also guiding the moon in its orbit around the Earth. Newton called it universal gravitation. Every mass attracts every other mass. The larger the mass and the closer the distance, the stronger the attraction. Newton did something astonishing. He turned the night sky into an equation. His law predicted the motion of planets with incredible accuracy. For the first time, the universe felt like a machine whose gears could be calculated. Reality was no longer ruled by divine purpose. It was ruled by mathematics. But Newton's gravity had a strange problem. He believed gravity acted instantly, across any distance. Tug the Earth, and the Sun would feel it immediately, even though they are separated by nearly 150 million kilometers. To Newton, this made sense. To many others, it felt like action at a distance bordered on magic. Still, the theory worked. For more than 200 years, Newton's equations explained almost everything we could measure. Almost. With the arrival of the 20th century, instruments grew more precise. Astronomers noticed something odd. The orbit of Mercury was drifting in a way Newton's law could not quite explain. The model that once seemed perfect began to crack. It took a young patent clerk named Albert Einstein to reveal why. Einstein's insight was radical. Gravity was not a force at all. He imagined the universe not as a stage where events take place, but as a fabric. Space and time were not separate. They were woven together into a single entity called spacetime. Massive objects warp this fabric. Smaller objects follow the curves in the fabric. We fall not because the sun or the earth pulls us, but because the shape of space-time guides our motion. In this view, the planets orbit the sun for the same reason a marble rolls around a depression in a stretched sheet. They are following the geometry of the universe. Einstein's equations described this curvature using a set of field equations published in the year 1915. They were tested in 1919 during a solar eclipse. Stars near the edge of the sun appeared slightly shifted, exactly as Einstein predicted. Light followed the curve of space-time. Gravity bent starlight. Einstein replaced the idea of a force with a deeper picture of reality. The universe was no longer a machine of invisible pulls. It was a sculptor shaping the flow of time itself. For more than 100 years, this paradigm ruled physics. From black holes to the expansion of the cosmos, general relativity described everything at enormous scales. Engineers could calculate satellite trajectories. Cosmologists could map the history of the universe. Einstein's theory passed test after test. Yet, in the quiet, outer reaches of galaxies, something did not add up. Astronomers like Vera Rubin observed how stars orbit the centers of galaxies. According to Newton and Einstein, stars farther from the center should move more slowly. After all, they are farther from most of the mass. But Rubin found the opposite. The stars on the outskirts moved just as quickly as those near the center. According to the laws of gravity we knew, those galaxies should have flown apart. It was as if gravity was stronger than it should be. The answer that emerged became one of the biggest mysteries in modern science. Physicists proposed something unseen. A new form of matter that does not reflect light or interact with electromagnetism. It would be everywhere. It would outweigh normal matter by a factor of 5 to 1, and it would provide the extra gravitational pull missing from our equations. They called it dark matter. The idea was bold. It also worked. Simulations that included dark matter reproduced the structure of galaxies and galaxy clusters. Without it, the models failed. Observations of gravitational lensing in galaxy clusters seemed to show invisible mass bending spacetime. Dark matter became the leading explanation. There was only one problem. No one could find it. Physicists built detectors deep underground to shield them from noise. They sent satellites into space. They collided particles at enormous energies. Decades passed. The result was always the same. Nothing. No confirmed detection. No particle to claim the name dark matter. If dark matter were real, nature was hiding it extremely well. And so a new question emerged. A dangerous question. What if we are not missing matter? What if we are missing something deeper? The idea that gravity might need to be revised felt almost heretical. Gravity is the oldest force we think we understand. It guided Newton. It curved spacetime for Einstein. It matches observations on enormous scales. But in the edges of galaxies, it behaves like a riddle. Maybe gravity is not what we thought. Maybe it is not a fundamental feature of the universe. Perhaps gravity is not a force. Perhaps it is something that emerges from something deeper. The first hint came from an unexpected place. Not from motion, not from mass, but from heat, from information, and from entropy. If this is true, then everything we know about gravity might only be the shadow of something more fundamental, something woven into the fabric of reality itself, something that does not pull, something that emerges. If gravity is not a fundamental force, then something else must be whispering through the structure of the universe, guiding the dance of planets and stars. To uncover that something, physicists turned to the most unlikely places. They studied the hottest objects ever conceived, the cold emptiness between galaxies, and the silent mathematics of information itself. The journey did not begin with gravity. It began with thermodynamics, the study of heat. In the 1970s, a young physicist named Jacob Bekenstein had an outrageous thought. Black holes, those regions where space-time collapses and nothing escapes, might not be the perfectly silent monsters we believed. They might contain entropy. Entropy measures information, or more precisely, the lack of information. If you throw a priceless book into a black hole, all the structure and meaning in its pages vanish. The information that once existed is gone from our universe. Bekenstein argued that the black hole must store that information in some way. Otherwise, physics itself would break because one of the deepest principles in science is that information cannot be destroyed. Stephen Hawking disliked the idea at first. He insisted that black holes erase everything. No information could possibly escape. But when Hawking performed the calculation, he discovered something stunning. Black holes emit radiation. They glow ever so faintly, like a perfect body of heat. That glow became known as Hawking radiation. It revealed a crucial fact. Black holes have entropy, and the amount of entropy they contain is not proportional to their volume. It is proportional to the area of the surface that surrounds them. This was the first time physics whispered a dangerous possibility. The universe stores information on surfaces, not in volumes. Reality behaves like a kind of hologram. The idea matured in the 1990s when the physicist Ted Jacobson asked a question no one else had dared. If black holes behave like thermodynamic systems, could the same be true for space-time itself? Jacobson treated the fabric of space-time the same way 19th century scientists treated steam in engines. He applied the basic rules of heat and entropy to tiny patches of space-time. When he finished the calculation, something shocking happened. Einstein's equations, the very equations that describe the curvature of space-time and the phenomenon we call gravity, emerged naturally from thermodynamics. This was not a trick. It was not a mathematical coincidence. Jacobson's result suggested that the geometry of space-time, and therefore gravity, arises from the statistical behavior of microscopic information. Gravity might not be fundamental. It might be a side effect of entropy. The implications were enormous. It meant that gravity could be similar to temperature. No one thinks of temperature as fundamental. Temperature exists because atoms move and collide. In the same way, gravity might exist because tiny units of information rearrange themselves. When their arrangement changes, space-time curves. We only feel the curve as gravitational attraction. Still, the idea was incomplete. Jacobson revealed that Einstein's theory could be derived from entropy, but he did not explain what that underlying information was made of. Space seemed to hold secrets even deeper than its curvature. The universe appeared to be storing bits of information the way a hologram stores an image on a flat surface. The next breakthrough came from the world of string theory. Physicist Juan Maldacena proposed that our universe might be described by a lower dimensional system living on a boundary far away. He called his idea ADS-CFT, short for anti-de Sitter conformal field theory. In simple language, he suggested that all the information in a region of space can be encoded on a distant surface. Space itself might not exist in the way we imagine. It might be constructed from quantum entanglement, the mysterious connection between particles that persists across any distance. In 2010, physicist Mark van Ramsdonk pushed the idea further. He showed that if you increase quantum entanglement, space-time becomes smooth and connected. If you decrease entanglement, space-time begins to tear apart. Space might not be the stage where entanglement happens. Space might be the thing that entanglement builds. If entanglement builds space, and Jacobson showed that entropy generates gravity, then gravity may not be a force at all. It may be the natural result of information trying to reach equilibrium. Still, the most dramatic step came from Erik Verlinde. In 2011, he proposed something bold. Gravity is not fundamental. It is an entropic effect. When matter changes the distribution of information in the universe, the system naturally seeks equilibrium. The tendency of information to spread out and maximize entropy is what we feel as gravity. Think of a rubber band. The tension you feel in the band is not a fundamental force. It is the collective behavior of countless molecules trying to return to equilibrium. Gravity could be the same. When a mass appears, it disturbs the information encoded in space-time. The universe responds. The response is what we have always called gravity. Verlinde went further. He suggested that what astronomers call dark matter might not be matter at all. The unexplained gravitational effects in the outskirts of galaxies might be a sign that gravity behaves differently at large scales, because entropy behaves differently at large scales. Instead of inventing a new invisible substance, perhaps we need to understand gravity as emergent from information. This idea gains power from a single fact. In 40 years of searching, no experiment has ever confirmed the existence of dark matter particles. Not in underground detectors, not in cosmic rays, not in particle accelerators. Astronomers see gravitational effects they cannot explain, but they do not see the stuff that should be causing them. Maybe there is no stuff. Maybe gravity changes because the structure of space-time changes. These ideas are not yet proven. They are debated fiercely in physics today. But they offer a path to unify quantum mechanics and gravity. They suggest that space-time is not a smooth, continuous fabric. It is woven from threads of information, and gravity is simply the tension in that weave. The chapter began with Aristotle and the idea that stones fall because they want to be on the ground. For 2,000 years, that idea endured until experiments proved otherwise. Newton replaced purpose with universal law. Einstein replaced force with curvature. And now we stand at another threshold. Perhaps gravity is not a command written into the universe. Perhaps gravity is the universe remembering. Astronomy is not done in silence. It is done in doubt. Every observation whispers a possibility that something we believe might be wrong. For centuries, gravity was the most reliable idea we possessed. Newton gave us a universe of precise motion. Einstein replaced the concept of force with the curvature of space-time. Together, they described the arc of a falling apple, the orbit of the moon, the light of distant stars bending around massive clusters. The mathematics worked so beautifully that physicists began to treat gravity as finished, understood, solved, but the universe refuses to be solved. During the middle decades of the 1900s, astronomers began to notice something strange. Spiral galaxies seemed to spin in a way that violated our expectations. These galaxies are vast islands of stars, each containing hundreds of billions of suns. They are arranged like enormous cosmic whirlpools. The laws we inherited from Newton say that stars near the center of the whirlpool should move faster than stars near the edge. After all, the mass near the center creates most of the gravitational pull. As distance increases, the gravitational influence of that mass becomes weaker. Therefore, the outer stars should move more slowly. That is what the equations demand, but that is not what the universe does. In the 1970s, an astronomer named Vera Rubin set out to measure the rotation curves of spiral galaxies. Rubin was patient, precise, and stubborn in the best scientific way. She did not assume answers. She collected data. She spent cold nights guiding a spectrograph at the Kitt Peak National Observatory, measuring the tiny Doppler shifts in starlight to determine how fast those distant stars were moving. She expected to see decline. She expected the outer stars to slow. They did not. The stars far from the galactic center were moving just as fast as the stars near the middle. According to the laws of Newton and Einstein, these galaxies should have been flinging their outer stars into intergalactic space like sparks from a grinding wheel. Yet nothing flew away. The stars held their orbits, as if an invisible hand was gripping them tightly. Something was wrong. Rubin shared her results. The reaction was mixed. Some physicists questioned the measurements. Others insisted that dust clouds or observational error must be hiding the expected slowdown. But observation after observation told the same story. Galaxies across the universe were behaving in defiance of known gravitational law. the problem did not end with rotation curves. Astronomers studied galaxy clusters, immense gatherings of hundreds or thousands of galaxies. They measured how fast the galaxies were moving inside those clusters. They compared these speeds with the gravitational pull expected from the visible mass. Once again, the calculations failed. The galaxies inside these clusters were moving far too quickly to remain bound by the gravity of what we could see. Either gravity was stronger than we understood, or the universe contained far more mass than our telescopes could detect. Physicists reached for a solution that preserved the elegance of relativity. They proposed the existence of an unseen form of matter. Perhaps most of the mass in the universe was invisible. It would not reflect or absorb light. It would not interact with electromagnetic radiation. It would hide completely from our instruments except through gravity itself. They called it dark matter. To many scientists, dark matter felt like a rescue mission. It allowed Newton's and Einstein's laws to remain untouched. It patched the gap between theory and observation by adding something new to the universe. Invisible mass. Invisible particles. A new kind of matter that did not play by the rules of ordinary atoms. It worked astonishingly well on paper. When simulations of galaxy formation included dark matter, the cosmic structures that emerged looked almost identical to the observed universe. Dark matter became the scaffolding of cosmology, the invisible framework on which galaxies formed and grew. Yet there was discomfort hidden beneath the success. It felt suspiciously like a placeholder, a thing invented solely because gravity did not behave the way we expected. The search began. Large underground detectors were built to capture the faintest signature of a passing dark matter particle. Satellites were launched into orbit to search for hints in cosmic rays. Particle accelerators smashed atoms together at incredible energies, hoping to create dark matter in controlled conditions. Decades passed. Nothing appeared. The universe was quiet. Every negative result deepened the mystery. How could dark matter be so essential and yet remain so undetectable? Dark matter was meant to explain why galaxies rotate as they do. It was meant to explain the gravitational lensing we observe when massive clusters bend spacetime. But if this invisible matter was truly everywhere, why did not a single experiment confirm its existence? Some physicists suggested that dark matter might interact only through gravity, making it nearly impossible to detect. Others argued that the particles might be so heavy or so light that our instruments simply cannot sense them. More complicated models appeared. Dark photons, weakly interacting massive particles, sterile neutrinos. The explanations multiplied. The evidence did not. Science thrives when the universe agrees to play along, but when the universe refuses, doubt becomes fuel. In quiet offices and late-night conversations at conferences, a new question began to surface. A dangerous question, one that threatened the foundation of modern physics. What if there is no dark matter? What if the laws of gravity break down on large scales? Einstein taught us that spacetime curves in response to mass and energy. But Einstein never proved that his equations applied perfectly to the enormous scales of galaxies. He never intended his theory to explain the entire universe. He designed it to explain motion and light in strong gravitational fields, such as those near stars and planets. Perhaps something subtle changes when gravity stretches across hundreds of thousands of light years. Vera Rubin was once asked how she felt, knowing she had uncovered a mystery that challenged the neatness of physics. She simply smiled and said that the universe is always more imaginative than we are. The idea that gravity could fail was no longer unthinkable. It became necessary. Little by little, cracks in the old story appeared. Perhaps gravity did not need invisible matter to explain these galactic puzzles. Perhaps gravity itself needed to be examined again. The most surprising clues came not from telescopes, but from the realm of heat and entropy. While astronomers argued about dark matter, a few theorists quietly realized that the strange motion of galaxies hinted at something deeper. Gravity might not be a fundamental force at all. It might be something that emerges, like temperature emerges from atoms in motion. A universe built from information. A universe where gravity arises because entropy demands it. If this is true, then the problem is not that gravity fails. The problem is that we have been asking the wrong question. The idea that gravity might be incomplete did not begin with rebellion. It began with something much quieter: reluctance. Physicists are trained to trust the equations that have worked for centuries. Newton described the motion of planets with astonishing precision. Einstein revealed the geometry of spacetime with a clarity that reshaped modern science. It feels almost disrespectful to question something so elegant. Yet nature cares nothing for elegance. Nature cares only for truth. The truth was written in the rotation curves of distant galaxies. If visible matter was the only thing shaping gravity, then galaxies would behave according to Newton and Einstein. But they did not. Astronomers kept trying to fix the galaxy curves using the old equations, like patching a cracked vase with more glue. Dark matter became that glue. A perfect answer because it fixed everything while leaving old theories untouched. But science moves forward when someone is willing to ask if the glue should be there at all. A small group of physicists began to consider an unsettling possibility. Maybe the extra gravity observed in galaxies does not come from extra matter. Maybe it comes from the laws of gravity behaving differently on enormous scales. If gravity changes across large distances, we would see stars in the outskirts of galaxies moving too fast without needing any hidden mass. The first serious attempt to modify gravity on cosmic scales was called modified Newtonian dynamics. It proposed that when gravitational acceleration becomes extremely small, much smaller than anything we could test inside our solar system, gravity behaves differently from Newton's law. It was surprisingly successful at predicting the rotation speeds of stars in spiral galaxies. But it struggled to explain other observations, especially those involving galaxy clusters. Then came the bullet cluster, one of the most dramatic pieces of evidence in the entire debate. Two massive clusters of galaxies collided, and astronomers observed the aftermath. The glowing gas that makes up most of the visible matter was slowed by the collision, heating up and emitting high-energy light. But the gravitational influence, revealed by the bending of space-time, did something strange. It did not stay with the gas. It moved ahead, as if the gravity were following something invisible that continued straight through the collision. To many physicists, this was the smoking gun for dark matter. Invisible mass seemed to behave independently of visible matter. Still, there was a catch. The bullet cluster told us gravity was responding to something we could not see, but it did not tell us what that something was. Gravity revealed an imprint. It did not reveal the source. And in science, an imprint is not proof. Time passed. Experiments continued. Underground detectors waited in silence for a single dark matter particle to collide with their sensors. None did. Large particle colliders searched for clues among debris from high-energy collisions. None appeared. Space-based telescopes scanned the sky for anomalies that would betray the decay of dark matter particles. Nothing emerged. The silence became louder than any signal. Meanwhile, another revolution was taking shape far from observatories. In theoretical physics, black hole research was leading to a strange conclusion. Information seemed to play a deeper role in the universe than matter or energy. When black holes swallow objects, they do not increase in volume. They increase in surface area. Their entropy is stored on their outer boundary. This behavior contradicted everything we expected. Volume is where matter should accumulate. Yet black holes care only about area. What if the universe itself behaves this way? If the cosmos stores information on surfaces, and if gravity is tied to information, then perhaps the excess gravitational pull in galaxies is not caused by hidden mass. It might be caused by hidden information. This idea gained strength when researchers realized that spacetime behaves like a thermodynamic system. Ted Jacobson demonstrated that Einstein's equations describing the curvature of spacetime can be derived from the laws of heat flow and entropy. It was a shock. Something as majestic as gravity could be explained through something as ordinary as thermodynamics. In that moment, gravity began to look less like a law of nature and more like an emergent phenomenon. Emergent phenomena are not fundamental. They arise from simpler ingredients. Temperature is not a fundamental property of reality. It emerges from the average motion of countless molecules. The smoothness of water is not fundamental. It emerges from the collective behavior of trillions of atoms. We do not feel each atom, we feel the whole. Gravity might be the same. We do not feel the individual bits of information that make up space-time. We feel the collective effect. When this idea collided with the mystery of galactic rotation, a daring possibility formed. Maybe the unseen gravity in galaxies is not dark matter. Maybe it is the result of additional entropy stored in the fabric of space-time itself. The universe may be doing what thermodynamic systems always do. It may be trying to maximize entropy, to reach equilibrium. And the motion of stars could be a visible side effect of that process. This possibility challenges a deep instinct. Humans prefer material explanations. If something pushes or pulls, we imagine a substance doing the pushing or pulling. Dark matter fits that instinct perfectly. Gravity is stronger than expected, so there must be more mass. It is the same instinct that led ancient philosophers to fill empty space with invisible ether so that light would have something to travel through. But sometimes, nature is not hiding more stuff. Sometimes nature is hiding deeper law. The idea that gravity might emerge from entropy does not require new particles, new forces, or unseen matter. It requires only the information already woven into the universe. It requires only that space-time is not a smooth fundamental fabric, but a structure built from microscopic degrees of freedom. It requires that gravity is what happens when that structure tries to rearrange itself. This is a bold shift. But when existing theories fail to explain observation, bold shifts become necessary. Einstein himself rewrote gravity when Newton failed to describe Mercury. He once said that imagination is more important than knowledge. Imagination reveals what knowledge has not yet grasped. The unanswered question remains: why do stars on the edges of galaxies refuse to slow? Why do galaxies hold together when mathematics says they should fly apart? If invisible matter exists, decades of searching should have found it. If gravity is complete, there should be no cracks. Instead, we find cracks everywhere. Perhaps gravity is showing us that what we call empty space is not empty. Perhaps the universe is not made of matter embedded in space-time. Perhaps the universe is made of information, and space-time emerges from it. And perhaps gravity is the whisper of that information as it moves toward equilibrium. It is not that gravity fails, it is that gravity reveals something deeper. Black holes are the most extreme objects the universe allows. They are regions where space-time caves inwards so deeply that nothing, not even light, can climb back out. For a long time, physicists imagined black holes as perfect swallowing pits. Anything that crossed the event horizon was gone forever, erased from existence. In those days, black holes were treated like the ultimate garbage disposal of the cosmos. No information escapes, no energy leaks out. Silent, absolute. But silence is suspicious in science. In the early part of the 1970s, a young physicist named Jacob Bekenstein began to wonder if that view could be wrong. Bekenstein had the unsettling habit of noticing problems in ideas everyone else considered solid. He believed black holes must have entropy. Entropy measures disorder, but more deeply, entropy measures information. When you burn a book, the words are lost to you, but the information is not destroyed. It is scattered into smoke and heat and light. The universe keeps its accounting perfect. Information cannot vanish. So Bekenstein asked the question that no one else dared. What happens to information when it falls into a black hole? If the information is gone, then one of the most sacred rules of physics is broken. If the information remains, then black holes cannot be the featureless pits we once imagined. Stephen Hawking tried to disprove Bekenstein. He performed the calculations precisely and discovered the opposite. Black holes emit radiation. They are not quiet. They are not perfect prisons. They glow with what is now called Hawking radiation, the faint thermal light that escapes from just outside the event horizon. And because they radiate heat, they must contain entropy. The shocking realization was not that black holes have entropy. The shock was where that entropy is stored. It is not proportional to the black hole volume. It is proportional to the surface area of the event horizon. The more area the horizon has, the greater the entropy. Think about that. Every physical system we know stores information in its volume. A box of gas contains information in every cubic centimeter of space. A black hole stores information only on its surface. It was as if the universe were whispering a secret. Information lives on surfaces. This area law became the seed of a far deeper idea. If black holes store information on their boundaries, perhaps the universe does the same. Perhaps what we call space is not where information lives. Perhaps space is what information creates. The connection between information and gravity became stronger in 1995, when physicist Ted Jacobson made a stunning leap. He wondered if spacetime itself might behave like a thermodynamic system. Thermodynamics began in the age of steam engines. Engineers discovered that heat, pressure, and work follow strict mathematical rules. Those rules do not care what the engine is made of. You can build it out of metal or wood. The behavior is the same because thermodynamics is about collective behavior of countless molecules. Jacobson imagined that spacetime might work in the same way. Instead of steam molecules, he worked with small pieces of spacetime and asked what happens when energy flows across them. If the universe obeys thermodynamics, then the change in entropy should relate to the heat flow. Jacobson wrote down the basic thermodynamic equation that governs heat exchange and linked it to the flow of energy through the fabric of spacetime. When he solved it, Einstein's field equations emerged. That moment changed everything. Einstein spent years discovering the geometry of the universe. Jacobson derived that geometry using nothing more than the laws of thermodynamics. It meant that the curvature of spacetime, the very thing we feel as gravity, was not fundamental. It was the collective behavior of deeper microscopic elements. The universe behaves like an engine. Space-time behaves like a fluid made of something tiny and unknown. Gravity is not a force. It is the natural result of entropy increasing as information spreads out. This revelation shook the foundations of physics. Einstein's equations no longer looked like commandments of the universe. They looked like statistical outcomes. The same way temperature is not fundamental, but arises from countless molecules in motion. No one feels one molecule. We feel their collective push. No one feels one bit of space-time information. We feel the curve they create. But if gravity is emergent from statistical behavior, what are the microscopic pieces? What are the underlying building blocks of space-time? The universe answered with something even stranger than entropy. It answered with entanglement. Entanglement sounds like magic, until you realize it is simply how quantum particles keep their accounts. When two particles become entangled, their properties are linked no matter how far apart they travel. Measure one, and you instantly know something about the other. Einstein called this spooky action at a distance. He disliked it, yet experiments have proven it again and again. Entanglement is not a footnote of quantum theory. It is the spine. Now imagine that the entire universe is built from these relationships, not from particles themselves, but from the information that describes how particles are connected. Entanglement becomes the thread that stitches space together. Where there is strong entanglement, space is smooth and connected. Where there is little or no entanglement, space frays, stretches, or tears. The fabric of space-time becomes a map of quantum information. This perspective changed everything because it revealed a strange consequence. If you know how entangled two regions are, you can calculate the area between them. Space becomes geometry, geometry becomes entropy, and entropy becomes the key to gravity. In 2010, physicist Mark van Ramsdonk demonstrated something astonishing. He imagined a universe that was fully entangled. In that universe, space-time was smooth and continuous. Then he gradually reduced the entanglement. As the entanglement decreased, the geometry of space-time started to pull apart. At the extreme, space-time tore into disconnected pieces. The lesson was clear. Entanglement does not just live in space. Entanglement creates space. Combine this with Jacob Bekenstein's discovery that black hole entropy lives on surface area, not volume. Combine it with Ted Jacobson's proof that Einstein's equations follow from thermodynamics. Suddenly, three strange facts, discovered decades apart, fit together like puzzle pieces. Entropy and entanglement determine geometry. Geometry is what we call space-time. And gravity is what happens when space-time curves. This is not mysticism, it is mathematics. It is what nature reveals when we listen closely. A black hole is the most obvious place to see these ideas working. Every time matter falls in, the event horizon grows. The surface area increases. That increase in area represents an increase in entropy. It represents an increase in information. The black hole is not eating matter. It is storing information, encoded on its surface. The universe seems to be telling us that information is more fundamental than volume. The boundary matters more than the inside. The physicist Juan Maldacena gave this idea its most famous form. He proposed that everything inside a certain kind of space could be represented by information on a distant surface. This concept became known as ADS-CFT. In simple words, it means that the entire three-dimensional world inside a region can be described by a two-dimensional system living on its boundary. The universe behaves like a hologram, and in a holographic universe, gravity cannot be fundamental. A hologram does not pull or push, it encodes. If space is built from information, and information has entropy, then gravity emerges from the way that entropy rearranges itself. This idea becomes even more powerful when we zoom out. Imagine a galaxy. Stars orbit around the center. According to Newton and Einstein, their speed should decrease with distance. But we know they do not. They maintain high speeds far from the center. To reconcile this without dark matter, we would need a new kind of gravity that becomes stronger, where space-time holds more hidden information, where entropy increases. This is where Erik Verlinde enters the story. Verlinde is a quiet kind of revolutionary. In 2011, he asked a question that seems absurd until you witness its power. What if gravity is an entropic force? Not a fundamental interaction like electromagnetism. Not a curvature that exists by itself. What if gravity arises because systems naturally move towards states of higher entropy? Picture a piece of elastic pulled tight. The tension you feel is not fundamental. It comes from molecules doing their statistical dance, trying to reach equilibrium. The elastic pulls back not because it chooses to, but because entropy demands it. Verlinde applied the same idea to the universe. When matter disturbs the distribution of information, the entropy of spacetime changes. The universe tries to restore balance. The restoring effect is what we experience as gravity. Gravity becomes a result of information trying to even itself out. Verlinde then went further. He suggested that the strange rotation of galaxies, the very observation that inspired dark matter, could be explained by additional entropy that appears on very large scales. This additional entropy would act like extra gravity without needing any invisible mass. This is not speculation. Verlinde derived equations that match observed galaxy rotation curves. They match without adding any unknown particles. They emerge from the mathematics of information and entropy. And the most striking part is that this idea does not contradict Einstein. It completes him. Einstein described how spacetime curves. Verlinde explains why it curves. If this perspective is correct, then space is not a stage. It is a structure woven from information. Time is not a ticking clock. It is the evolution of that information. And gravity is not a fundamental force. It is the universe following the most natural rule imaginable. Entropy increases. The second law of thermodynamics does not simply govern boiling water or melting ice. It governs space-time itself. The cosmos flows toward higher entropy. Stars orbit galaxies because space-time curves. Space-time curves because information rearranges. Information rearranges because entropy must grow. Every falling apple, every orbiting moon, every swirling galaxy is simply the universe taking the next most probable step. If this is true, gravity is not the oldest force we think we understand. Gravity is the newest illusion we are learning to see through. At first glance, the universe looks like a place made of things. Stars, planets, gas, dust, and the thin, invisible scaffolding of gravity that holds it all together. We grow up believing that matter is primary, that reality is built from particles, each one a tiny, indivisible bead. But over the last century, physics has whispered a different truth. The deeper we look into the structure of reality, the more matter fades away. What remains is not substance, but information. Information is not just something we store in computers or write in books. In physics, information means the number of possible states a system can be in. It is the measure of what is known and what is unknown. Information tells us how many ways the universe can arrange itself. When disorder increases, information spreads. When things become organized, information becomes concentrated and meaningful. This connection is so deep that entropy, the measure of disorder, is also a measure of information. The idea that information is physical was first explored seriously by Rolf Landauer. In the middle of the 1950s, Landauer worked at a research lab where questions about logic and computation were not abstract. They were engineering problems. Landauer realized something startling. Erasing information is not free. If you erase a single bit, if you take a piece of data and wipe it clean, the universe must pay an energy cost. The act of forgetting produces heat. This insight became known as Landauer's principle. It showed that information is not an idea hovering in some mathematical space. Information has weight. Information has energy. When you delete information, you generate heat. You warm the world simply by choosing to forget. If information carries energy and energy curves space-time, then information must influence gravity. The moment that connection was recognized, the foundations of physics began to shift. We could no longer treat information as a mental concept. It had become a physical ingredient of the universe. To understand why this matters, imagine an empty region of space. We picture emptiness as a void, passive and silent. But emptiness in quantum physics is restless. Even a perfect vacuum seethes with activity. Fields fluctuate. Virtual particles appear and annihilate in fleeting moments. Space is not empty. Space contains information. If information is present even in the vacuum, and if information has energy, then the vacuum itself shapes gravity. Reality becomes a conversation between entropy and geometry. This strange new world became even stranger when physicists discovered the holographic principle. The idea was born when researchers studying black holes realized something shocking. The amount of information a black hole can hold is not proportional to its volume. It is proportional to the area of its surface. One side of a page stores the entire encyclopedia of everything that falls into it. Nature is telling us that information lives on surfaces. Gerard T. Hooft and Leonard Susskind took this idea to its fullest implication. They argued that everything inside a region of space could be encoded on the surface that surrounds it. The universe behaves like a hologram, where the interior is reconstructed from data on a two-dimensional boundary. Space, the very thing we move through, may be an illusion created by information stored on a cosmic screen. This is not metaphor. It is mathematics supported by black hole physics, quantum field theory, and string theory. The holographic principle suggests that the true description of the universe may not exist inside space at all. It exists on the edges. Once information became the foundation, entanglement, the ghostly link between quantum systems, revealed its power. Entanglement creates correlations that do not depend on distance. Two particles can be separated by the width of a continent or by the width of a galaxy. Measure one and the other responds instantly. These correlations are not carried by signals. They are woven into the structure of reality. Entanglement links information. Linked information shapes entropy. Entropy shapes space-time. And space-time gives rise to gravity. If all of this is correct, then gravity is not the fundamental author of motion. It is the narrator of a deeper story. Every time two particles become entangled, a tiny thread is added to the fabric of space. Every time entanglement increases, space becomes more connected. If the entanglement is cut, space thins and stretches. If enough entanglement vanishes, space can rupture entirely. Space does not contain information. Information constructs space. The more physicists studied entanglement, the more it looked like the foundation of geometry. The more they studied entropy, the more it looked like the driving force of gravity. And beneath both, the more they studied information, the more it looked like the fundamental currency of reality. A bridge forms between the microscopic world of quantum mechanics and the grand architecture of general relativity. The bridge is made of information. The curve of space-time, the pull we call gravity, and the motion of galaxies may all arise from the same principle. Information spreads. Entropy increases. The universe seeks equilibrium. It is no longer accurate to imagine gravity pulling objects together. Instead, picture the universe attempting to balance its information. Matter changes the distribution of information. The distribution of information shapes the curvature of space. Objects move along that curve not because they are pushed or pulled, but because that curve is the most probable path allowed by entropy. In this view, gravity is not a law, it is a habit of the universe. From the falling apple to the orbit of the moon, from the swirling arms of a galaxy to the surface of a black hole, every dance in the cosmos is merely the universe rearranging its information into the most probable pattern. Gravity is not the cause. Gravity is the consequence. The deeper we look, the less the universe resembles a machine of matter and forces. Instead, it resembles something far stranger. It resembles a computation, a continual processing of data, a flow of information across a cosmic screen. If this is true, then reality is not made of particles. Reality is made of choices. If information builds space, and if entropy shapes gravity, then what is matter? What is energy? What are the things we once believed were fundamental? In the old picture of physics, matter was primary. In the new picture, matter becomes secondary. It becomes a manifestation of information arranged in a particular pattern. A particle is not a tiny bead. It is a knot in a field of information. A star is not a ball of hot plasma. It is a place where information is dense enough to create curvature in space-time. Even you and I are not made of solid substance. We are arrangements of information that briefly take shape before dissolving back into the universe. Imagine standing on a mountain at night. The sky is dark, a velvet ocean with countless points of light. Every star you see is a furnace of fusion, burning hydrogen and forging heavier elements. Yet what you are truly seeing is a pattern of information. Every photon that reaches your eye carries a tiny bit of data about where it came from and how far it has traveled. When those photons strike your retina, a cascade of electrical signals flows to your brain. Your neurons interpret them. The night sky becomes a picture. All of it depends on information being preserved across unimaginable distances. The universe behaves as if information cannot be lost. When matter falls into a black hole, the black hole grows. Its surface area increases. Its capacity to hold information increases. It does not swallow information and erase it. It stores it. When Hawking discovered that black holes radiate, he began a crisis of logic. If a black hole evaporates, what happens to the information it holds? The holographic principle suggests that the information remains encoded in the radiation, just as a hologram stores a full three-dimensional image on a two-dimensional surface. This is where the idea becomes almost unsettling. If everything that exists can be described by information on a surface, then the reality we experience may be a projection. Not an illusion in the sense of being unreal, but an illusion in the sense of being derived. Just as a hologram on a sheet of plastic generates the illusion of depth, the universe may generate the illusion of space. The holographic idea becomes even more profound when we examine quantum entanglement. Entanglement does not care about distance. It acts with no regard for the speed of light. It does not transmit signals. It reveals that the universe is connected at a deeper level than geometry. Two particles separated by billions of kilometers can remain linked. They share information instantly because they are not truly separate. They are expressions of the same underlying informational structure. This challenges our intuition because we are used to a world of objects. We picture the universe as a collection of things moving through space. But if entanglement creates space, then space is not a container for matter. Space is the relationship between informational states. Where relationships are strong, space is short and connected. Where relationships are weak, space stretches. Where no relationship exists, space may not exist at all. Consider a sheet of fabric. If every thread is woven tightly, the fabric is smooth and strong. If the threads loosen, the fabric distorts. If enough threads are removed, holes appear. Entanglement is the weaving. Space is the fabric. Gravity is the tension that emerges from the arrangement of the weave. This idea does more than inspire wonder. It solves puzzles. In the traditional view, gravity simply is. It has no deeper explanation. It is like accepting that the ocean has tides without knowing that the moon pulls water. In the emergent view, gravity becomes a side effect of entropy. When information increases, when entanglement redistributes, space-time responds. Objects move because entropy is guiding the shape of space. They are not pulled. They are guided toward the most natural state of the system. The falling apple does not obey a law because gravity commands it. The apple follows a path that increases entropy. The orbit of the moon is not enforced by a force. It is permitted by the geometry of information. The motion of galaxies does not require invisible matter holding them together. It may simply require that space-time stores more information than we once imagined, giving rise to extra entropic effects that appear as missing mass. There is something beautiful in this perspective. It means that the universe is not a machine. It is not a cold engine grinding blindly through equations. The universe is a story written in bits of information, continually rearranging itself into states of greater possibility. Motion is not caused. Motion is allowed. Physicists used to believe that reality would grow simpler the deeper we looked. They believed that if we kept dividing matter into smaller pieces, we would eventually find the ultimate building block. But every time we reached what we thought was the bottom, we found something deeper. First molecules, then atoms, then protons and neutrons, then quarks, then quantum fields. Now we stand before the most radical shift yet. There may be no objects at the bottom of reality. There may be only information. When you drop a stone into a lake, ripples move across the water. You do not ask what the ripples are made of. They are patterns of motion in the water itself. The stone is not pushing the ripples. It is disturbing the surface, and the surface responds. In the same way, mass is not pulling on space. Mass disturbs the informational structure of space-time, and the structure responds. The response is what we call gravity. Information is not an accessory to physics. Information is the foundation. Everything we see, everything we touch, everything we believe to be real may be the surface expression of a deeper informational order. And gravity, the oldest force we think we understand, may simply be the universe tending toward the state with the highest entropy. In that sense, the universe is not a place of things. The universe is a place of meaning. For centuries, gravity has demanded reverence. Newton described it with a single elegant equation. Einstein reshaped it into the curvature of space-time. Every generation polished the idea further until gravity felt complete. It felt as if no great surprises remained. Yet, in the early years of the 21st century, a quiet revolution began inside the mind of a Dutch theoretical physicist named Erik Verlinde. He did not start with rebellion or with the desire to overthrow Einstein. He started with a simple question: what if gravity is not a fundamental force at all? Verlinde was not an outsider. He was celebrated for his work in string theory and for contributions to the holographic principle. He knew the language of black holes and information. He understood the mysteries of entropy. But while others were content to apply these ideas to the edges of physics, Verlinde followed a different scent. He suspected that the connection between entropy and gravity was not a coincidence. It might be a window into the deepest architecture of reality. He began with something ordinary, a box filled with gas. In thermodynamics, the molecules inside always move in ways that maximize entropy. They spread out, searching for the most probable configuration. No one molecule knows what the others are doing. There is no leader. There is no purpose. Yet from the collective motion of countless particles, a macroscopic effect emerges. We call that effect pressure. Pressure pushes pistons in engines and shapes weather patterns. Yet pressure is not fundamental. It is a consequence. Verlinde asked if gravity could be like that. Not a fundamental force that reaches across the universe, but a consequence of a deeper statistical process. In thermodynamics, forces sometimes appear not because something is pushing, but because the system seeks equilibrium. When you pull a rubber band, the tension is not a fundamental property. It comes from the random motion of molecules that prefer disorder. The rubber band resists your pull because entropy demands it. Verlinde realized that gravity behaves exactly like this. When two masses move apart, information about their separation changes. The entropy of space-time changes. And just like the rubber band, nature tries to restore balance. The restoring tendency is what we interpret as gravitational attraction. Objects do not fall because gravity pulls. Objects fall because the universe prefers states of higher entropy. This idea, radical as it is, perfectly matches everything known about information and black holes. The discovery that black hole entropy scales with surface area tells us that information lives on boundaries. Entanglement determines geometry. Geometry determines curvature. Verlinde followed this chain of reasoning to its inevitable destination. Gravity is the thermodynamic response of spacetime to changes in information. He published the idea in the year 2011. Instead of treating gravity as a fundamental force like electromagnetism, he treated it as an entropic effect. In the same way that heat produces pressure, entropy produces gravity. He described how the motion of masses disturbs the information encoded in spacetime. Then he used the mathematics of thermodynamics to show that the restoring effect, the push toward equilibrium, takes the same form as Newton's law of universal gravitation. Newton found the law by observing motion. Verlinde found the same law by analyzing information. It was an earthquake inside theoretical physics. Not because it broke Einstein's equations, but because it explained why those equations exist. Einstein showed how spacetime curves. Verlinde showed why spacetime must curve. He changed gravity from something that commands the motion of matter into something that emerges from the deepest bookkeeping of the universe. For a physicist, this is a revelation. It means that mass does not cause gravity because mass has a mysterious property called gravitational charge. Mass causes gravity because mass changes information. Gravity is not a verb. Gravity is a consequence. Imagine a planet orbiting a star. In the traditional view, the star pulls the planet. In the entropic view, the presence of the star changes the configuration of microscopic information in spacetime. The planet moves because moving increases entropy. The path of orbit is not forced. It is permitted. It is the most statistically favorable arrangement. This idea becomes even more striking when applied to cosmic scales. In spiral galaxies, stars at the outer edge travel much faster than expected. Instead of slowing as Newton predicted, they maintain speed as though an extra gravitational influence exists. The traditional fix is to invent invisible mass. Dark matter becomes the ghostly scaffolding that holds galaxies together. But what if no ghost exists? What if spacetime itself stores extra information when probed on enormous distances? In 2011, Verlinde proposed that this additional gravitational effect is entropy, not matter. The idea was elegant and terrifying. It required no new particles, no hidden mass. It required only that information has structure and that gravity is the system's response to that structure. Gravity becomes an emergent thermodynamic effect, the way temperature emerges from molecular agitation. If this is correct, then the universe does not need invisible matter to explain galactic motion. It needs only the information contained in spacetime itself. At first, physicists were cautious. Some dismissed the idea as too philosophical. Others believed gravity must remain fundamental. Yet Verlinde was not guessing. He was using the same thermodynamic logic that allowed Ted Jacobson to derive Einstein's field equations. The same logic that allowed Bekenstein and Hawking to uncover the entropy of black holes. The same logic that motivated the holographic principle. There were no leaps of faith, only the mathematics of information. He knew that if gravity is emergent, then it must produce testable predictions. And he knew exactly where to look, because the outer stars of galaxies do not behave according to Newton or Einstein. They behave according to entropy. When a theory challenges something as old as gravity, it must face a trial far harsher than elegance. It must face observation. It must face the sky. After publishing his entropic gravity idea, Erik Verlinde went deeper. He realized that if gravity emerges from information, then spacetime must store more information when stretched over vast cosmic distances. In 2016, he released a refined version of his theory. Not only did it derive Newton's law from entropy, it also explained the missing gravity in galaxies. In Verlinde's model, when you look at a galaxy from far away, you are not just seeing stars, you are seeing a region of spacetime saturated with long-range entanglement. The larger the scale, the more information is stored. The more information stored, the greater the entropic response. That response appears as extra gravity, no dark matter required. The logic is simple but profound. Entanglement and entropy grow with distance. At galactic scales, they become significant enough to change how gravity behaves. The stars at the edge of a galaxy are not being held by invisible matter. They are being held by the informational structure of space-time itself. Verlinde wrote the mathematics to describe this. The equations predicted how much extra acceleration should appear in spiral galaxies. Then came the moment every bold idea fears. Someone tested it. Astronomers at the Leiden Observatory in the Netherlands collected data from more than 30,000 galaxies. They studied how the light of distant galaxies bends when it passes near massive objects. This bending, known as gravitational lensing, reveals how much gravity is present. It allows us to weigh galaxies without touching them. If Verlinde was wrong, lensing would show it. If gravity came from dark matter, the gravitational field would match dark matter models. But the data showed something different. The gravitational lensing around galaxies matched Verlinde's prediction. The signature that physicists attribute to dark matter appeared instead as a consequence of the entropic structure of spacetime. The galaxies behaved not as if they contained vast unseen matter, but as if gravity itself had changed. This result did not prove Verlinde's idea, but it gave it weight. It made the scientific world pause. Dark matter, after decades of searches, continues to leave no trace. Not one particle detected, not one direct interaction recorded. Experiments grow colder, sensors grow quieter, the silence grows heavier. The universe behaves as if something is causing extra gravity, but the something may not be matter. It may be information. Verlinde's theory also does something dark matter never could. It explains why the extra gravity appears only at low accelerations. In small systems like our solar system, the entropic contribution is negligible, so Newton and Einstein work perfectly. But at the enormous edges of galaxies, where gravity becomes very weak, the entropic response dominates. The boundary between ordinary gravity and emergent gravity is the boundary between local order and cosmic entropy. Still, the idea has critics. Dark matter fits comfortably in the standard model of cosmology. It predicts the formation of large-scale structure in the universe. It matches the map of temperature variations in the cosmic background radiation. It fits into computer simulations that match the universe we observe. Dark matter is the familiar answer. Verlinde offers a new one. But science does not reward comfort. The more physicists explored quantum information, the more gravity looked like a whisper of entropy rather than a fundamental force. Black hole entropy scales with surface area. The holographic principle encodes entire volumes on boundaries. Ted Jacobson derived Einstein's equations from thermodynamic laws. Mark van Raamsdonk showed that entanglement creates spacetime. Verlinde showed that entropic processes produce gravity. Pieces that once seemed unrelated began to converge. Gravity curves spacetime. Spacetime emerges from entanglement. Entanglement stores information. Information determines entropy. Gravity is the consequence of information arranging itself. The universe is not pushed by forces. it is guided by probability. This view does not shrink Einstein's legacy, it deepens it. Einstein saw gravity as geometry. Verlinde shows that geometry is born from information. Gravity becomes a shadow cast by entropy. Consider a drop of water forming a perfect sphere in microgravity. Surface tension is not fundamentally a sphere maker. It is a side effect of how molecules seek their most probable configuration. No one teaches water to form spheres. Water forms spheres because the rules of probability demand it. Gravity behaves the same way on the scale of space-time. No one instructs matter to fall. No invisible hand pulls stars around galaxies. Objects follow the path that increases entropy. They move into the most probable state allowed by information. If Verlinde is right, then gravity is not written into the universe as law. Gravity emerges from the universe as memory. The informational structure of space-time remembers where mass is, and the motion we observe is the result of that memory organizing itself. And if that is true, then gravity is not a force that must be unified with quantum mechanics. Gravity is what happens when quantum mechanics scales upward. It is not that gravity is wrong, it is that gravity is incomplete. In science, a mystery can survive for only so long before it demands a reckoning. The most persistent mystery in modern cosmology is the unseen influence called dark matter. For nearly 50 years, astronomers have watched galaxies spin too quickly. The stars at the outer regions move at speeds that defy both Newton and Einstein. Instead of slowing with distance, they race around the center as if gripped by an invisible mass. According to the gravity we know, those stars should escape into intergalactic space. But they do not. They remain bound. The traditional answer is simple. If gravity seems too strong, then there must be more mass. Since telescopes cannot see it, the mass must be invisible. Physicists gave it a name that captured their uncertainty. They called it dark matter. It became the silent majority of the cosmos, outweighing normal matter by about 5-1. Yet after decades of searching, not a single particle has been detected. No signal has appeared in underground detectors. No trace has emerged from particle collisions. It is as though the universe is holding a secret behind its back. Instead of adding new matter, Erik Verlinde looked at the problem from a different angle. He asked whether gravity itself changes on enormous scales. If gravity is not fundamental but emergent, as the thermodynamic view suggests, then its behavior should depend on how much information is stored in space-time. The farther you move from the center of a galaxy, the more space-time you include. That additional space-time carries additional entropy. Verlinde realized that at sufficiently large distances, the entropic influence becomes comparable to or stronger than the ordinary gravitational influence predicted by Einstein. In his 2016 publication, Verlinde presented a refined model. He did not assume dark matter. Instead, he calculated how much additional acceleration should appear if gravity emerges from the entropic tension of space-time. He began with the holographic idea that information is stored not in three-dimensional volume, but on surfaces. Then he considered what happens when matter sits inside that informational background. The presence of mass does not simply bend space-time, it disturbs the distribution of stored information. On large scales, the disturbance becomes significant enough to create extra gravitational strength. The astonishing part is that Verlinde did not tweak constants or invent new particles. He used only the mathematics of entropy. When he applied it to the rotation of galaxies, the predicted additional acceleration matched what astronomers observe. The mysterious flattening of rotation curves, the signature that built the entire idea of dark matter, emerged as a natural consequence of information. To test this idea, you need to weigh galaxies without touching them. Reality offers a perfect tool. When light passes near a massive object, Space-time curves and the path of the light bends. This bending is called gravitational lensing. It reveals the true gravity of an object, not just the gravity predicted from visible matter. In essence, gravitational lensing lets the universe reveal its weight. In the Netherlands, researchers at the Leiden Observatory used data from more than 30,000 galaxies. They measured how background light bends as it travels past these galaxies. If dark matter surrounds them, the bending should match dark matter predictions. If Verlinde is correct, the bending should follow the entropic gravity formula. The results lean toward Verlinde. The pattern of gravitational lensing fit the entropic prediction. This did not prove that dark matter does not exist, but for the first time, a model without dark matter matched real astronomical data on large scales. The success raised profound questions. If space-time stores information, and if gravity emerges from entropy, then dark matter may not be a physical substance. It may be a symptom of how information is arranged. The missing mass may instead be missing knowledge about the entropic structure of space-time. Still, caution is necessary. Dark matter explains more than galaxy rotation curves. It helps explain how galaxy clusters form, how structure grew in the early universe, and the delicate pattern of temperature variations in the cosmic background radiation. These observations do not yet fall neatly inside Verlinde's model. Dark matter has the advantage of tradition. It has been woven into simulations of the universe for decades. Verlinde's idea is newer. It must grow to match all cosmological observations. Yet the elegance of entropic gravity is difficult to ignore. It does not require invisible mass. It does not require special particles that evade detection. It does not require that most of the universe be made of matter we have never seen. It requires only that space-time has memory, that information is stored, and that entropy reacts. If this view is correct, then the universe becomes easier to understand. The stars orbiting the outskirts of galaxies are not being held by ghosts. They are being held by the structure of information. Imagine walking across a frozen lake. The ice appears solid, yet below the surface the water moves, currents shift, molecules flow. What you experience as solid ground is an illusion born from deeper motion. Gravity may be the same kind of illusion. It feels solid and fundamental because we live on the surface of space-time. But beneath that surface hides an ocean of information. The more astronomers look at the cosmos, the more they see patterns that point toward emergent gravity, regions where gravitational behavior changes at low acceleration, boundaries where entanglement begins to dominate, places where gravity behaves like a response, not a command. The possibility is daring. Gravity may not be a thing the universe does. It may be a thing the universe remembers. If mass disturbs information, and if information creates space-time, then gravity is not a force acting across space. Gravity is space correcting itself. And if that is true, then dark matter is not missing matter. Dark matter is missing understanding. Gravity is usually introduced to us as certainty. We learn that objects attract, that planets orbit stars, that space bends under the weight of mass. But certainty is fragile. It survives only as long as reality agrees. The deeper we look into the universe, the more gravity behaves like a language we have misunderstood. When astronomers extend their gaze beyond individual galaxies and toward clusters of galaxies, the puzzle intensifies. A cluster is a gathering of hundreds or even thousands of galaxies held together by a shared gravitational field. If ordinary matter were the only contributor to that field, then most clusters should be loose, fragile, and unstable. But many clusters are tightly bound. Something is providing extra gravity. The standard answer remains dark matter. Yet dark matter, as elegant as it is mathematically, continues to hide from every detector. It does not scatter, it does not collide, It does not reveal itself except through gravity. In Verlinde picture, this extra gravity does not come from particles. It comes from stored information. A galaxy cluster is not only a mass of stars. It is a web of space-time whose entropy is enormous. The moment information dominates over matter, gravity begins to emerge differently. The entropic contribution begins to outweigh the geometric curvature predicted by Einstein. The appearance of missing mass is simply the universe showing us that space-time is not passive. It is alive with structure. The most daring implication of Verlinde's idea is that space-time is elastic, not rigid, not fixed, elastic. Stretch space-time on small scales, and it behaves like Einstein's smooth fabric. Stretch it on immense cosmic distances, and hidden information reveals itself as added gravitational influence. Something similar happens in materials on Earth. A thin rubber sheet stretched gently behaves like a simple surface. But stretch it enough, and the microscopic structure of its molecules begins to matter. The rules change. The same is true for gravity. We have been measuring gravity only in conditions where its behavior is simple. Galaxies push us into the regime where space-time reveals its internal complexity. There is a deeper beauty here. Verlinde's model explains why the transition to this new behavior occurs only at very low acceleration. Most of the universe we interact with, including our solar system, lies above that threshold. This is why the planets orbit the Sun exactly as Einstein predicts. Emergent gravity does not replace Einstein. It extends him. Einstein described how mass curves space-time. Verlinde describes why curvature appears at all. For a moment, imagine following a single photon as it leaves a distant galaxy. It travels across hundreds of millions of light years, carrying only the tiniest quantum of information about where it has been. As it passes near another galaxy, its path bends. Not because it is pulled by an invisible force, but because space-time near that galaxy stores information differently. The photon chooses the path with the highest probability, the path where entropy increases. We experience that choice as gravity. The photon experiences it as inevitability. If gravity emerges from information, then we must shift the way we talk about reality. A planet does not warp space-time because it possesses gravitational mass. A planet alters the information structure of space-time, and the geometry we observe is the natural result. Entropy is not an optional ingredient. It is the rulebook that space-time obeys. This helps explain why the outer stars of galaxies behave so strangely. They are not racing faster than expected because something invisible holds them. They are racing faster because the informational richness of space-time increases as we include larger regions. The more space-time we consider, the more entropic tension accumulates. That tension acts like additional gravity. The idea sounds radical only because we are used to thinking of gravity as a fundamental force. But nature often hides emergent phenomena beneath layers of simplicity. Temperature is not fundamental. It arises from the motion of molecules. Pressure is not fundamental. It emerges from countless collisions. Surface tension, elasticity, rigidity, turbulence, magnetism in some materials, superconductivity at extremely low temperature, all appear only when many particles act together. They do not exist in a single particle. They emerge from collective interaction. Gravity may belong to that family. The universe may not need 4 fundamental forces. It may need 3 fundamental forces and 1 inevitable consequence of information. In this view, dark matter is not missing matter. It is a signal telling us that we have misinterpreted gravity. The universe speaks in entropy. Verlinde's model translates that language. Still, science must be disciplined. The entropic explanation works beautifully for galaxies. It fits the lensing data of entire populations of galaxies. But the universe contains more clues than rotation curves. The cosmic background radiation, the delicate speckled pattern left from the birth of the universe, also contains signatures that support the dark matter hypothesis. Emergent gravity must eventually explain those patterns or modify them in a way that still matches observation. This is how ideas survive. They are not defended, they are tested, and that testing continues. New data arrives from telescopes that map the distribution of galaxies. New surveys measure lensing across the sky. Future observatories will examine clusters at deeper resolution. Every measurement is a Yihai question. Does gravity behave the way Einstein wrote it? Or does entropy speak louder when distances stretch into the homes of galaxies? The James Webb Space Telescope has already revealed that early galaxies formed far earlier and far more efficiently than models predicted. That discovery shakes the scaffolding of dark matter as much as it emboldens the entropic view. The universe keeps hinting that gravity at grand scales is stranger than we imagine. If spacetime is built from information, if information carries entropy, and if entropy generates gravitational behavior, then gravity is not a force at all. Gravity is a statistical outcome. The universe is not held together by invisible matter. The universe is held together by memory. When stars move, they follow the contours of information. When galaxies grow, they trace the pattern of entanglement. When space-time curves, it curves because probability bends. Dark matter once seemed like the missing piece of the universe. But perhaps the missing piece was gravity itself. Not the gravity we inherited, but the gravity that emerges. When physicists speak about the holographic universe, most people imagine something mystical or ornamental, a poetic metaphor dressed in scientific language. But the idea is neither decoration nor fantasy. It grew from a crisis caused by black holes. In the 1970s, Jacob Bekenstein showed that the amount of information a black hole can hold depends not on its volume, but on the area of its surface. This simple fact shattered the familiar sense of space. If volume does not determine how much information can exist inside it, then volume may not be fundamental. Space, as we experience it, might not be the basic ingredient of reality. A decade later, Stephen Hawking discovered that black holes emit radiation. With that discovery, the black hole gained a temperature and an entropy. It stopped being a mysterious tear in space-time and became a thermodynamic object. From that moment on, gravity could no longer be separated from heat, entropy, and information. The black hole was no longer a void. It was a storage device, holding information of everything that had ever fallen inside it. Even then, no one was prepared for what came next. Imagine a sphere. We are taught that everything that happens inside the sphere requires information stored throughout the three-dimensional volume. But black holes refused to follow that rule. They declared that only the surface matters. The interior is not where information resides. Reality stores information on boundaries. This strange behavior raised a disturbing question. If the laws of physics allow information to live on surfaces instead of inside volumes, could the entire universe follow that rule? Could all of space, all of motion, all of matter be a kind of projection created from information encoded on a distant boundary? Gerard T. Hooft proposed that this might be true for the universe as a whole. Leonard Susskind refined the idea and named it the holographic principle. In this view, the universe we move through is like the three-dimensional image produced by a hologram on a thin sheet. The sheet is two-dimensional, but it contains all the information needed to create the illusion of depth. The picture does not exist inside the sheet. It emerges from the information held on the sheet. Years later, Juan Maldacena gave the holographic principle a precise mathematical realization. He discovered that a universe with gravity in 3 dimensions can be described exactly by a universe without gravity on a 2-dimensional boundary. Every particle, every field, every gravitational curvature inside the volume corresponds to something happening on that boundary. Maldacena created a dictionary between spacetime and information. It was the first convincing demonstration that space may not be fundamental. If a hologram can create depth from a flat surface, then the universe may create space from information. Entanglement becomes the key. 2 regions of the universe can share quantum information. The amount of entanglement determines how those regions are connected. If entanglement is strong, space forms a smooth bridge between them. If entanglement weakens, space stretches and becomes thinner. If entanglement disappears entirely, space can break apart. In this view, distance is not an absolute feature of reality. Distance is a measure of how much information 2 systems share. To understand why entanglement matters, imagine 2 people holding hands in the dark. You cannot see them, but you know they are connected. Now imagine separating them farther and farther apart. As long as they hold hands, there is connection. If they let go, the link disappears. Entanglement is the quantum version of that holding of hands. The distance between 2 entangled particles does not matter. The connection remains. From those connections, space emerges. Mark van Ramsdonk made this picture vivid. He imagined gradually reducing the entanglement between 2 regions of space. As he removed the entanglement, the 2 regions began to pull apart. When enough entanglement vanished, space broke into separate pieces. In his calculation, entanglement built spacetime the way threads build fabric. Without entanglement, the fabric unravels. The holographic universe is not telling us that reality is fake. It is telling us that reality is encoded. What we experience as space is the expression of information. Gravity becomes a behavior that emerges from this information, not an intrinsic force. If space-time is woven from entanglement, then curvature and gravity are consequences of how the threads are arranged. The most unsettling part of the holographic idea is how ordinary our world feels. We wake up, walk through rooms, touch objects, think thoughts. Everything seems solid. But solidity is a sensory convenience. Matter feels solid not because it is impenetrable, but because the electromagnetic field resists overlap. Touch is simply repulsion translated into sensation. Sight is photons interacting with receptors. Sound is vibration through air. Every perception relies on information exchanged between systems. Nothing about our experience guarantees that space is fundamental. The holographic principle forces a reversal. Instead of asking how information fits inside space, we ask how space emerges from information. When we do, the universe becomes simpler. Information is conserved. Entropy grows. Systems evolve towards states with higher probability. Spacetime behaves like a geometric representation of those statistical truths. Try to imagine the universe not as a stage, but as a network. Each node holds quantum information. Each connection represents entanglement. Space appears only where connections exist. Remove the connections and space evaporates. Add connections and space forms. Gravity becomes the result of how connections respond when matter changes the distribution of information. This picture is not philosophical speculation. It has mathematical structure. When Maldacena described how gravity inside a volume corresponds to information on a boundary, he revealed that the behavior of spacetime in the bulk is governed by entanglement on the surface. The equations of general relativity emerge from patterns of information. The geometry Einstein discovered arises from something deeper. And yet, even with this enormous shift, the the world looks the same at human scale. Apples still fall. The moon still orbits. Planets still follow elliptical paths. Nothing in our daily life reveals the informational engine beneath spacetime. The holographic universe is not obvious because the emergence of space is perfect. It hides its own construction. Only in extreme environments, like black holes or galaxies rotating faster than Newton predicts, does the illusion reveal its edges. There, the informational structure becomes visible through anomalies in gravity. These anomalies are what led Verlinde to propose that gravity is not fundamental. If space emerges from information, and if gravity emerges from space, then gravity is a secondary effect. It is not the architecture, it is the echo. This view dissolves the boundary between quantum mechanics and general relativity. The two were once incompatible, speaking different languages. But if space emerges from quantum information, then gravity becomes the macroscopic result of microscopic entanglement. Quantum mechanics stops conflicting with relativity. It becomes the foundation from which relativity emerges. If the holographic universe is real, the deepest truth about existence is that everything is information. We do not move through space. We move through relationships encoded in a network of entanglement. And when we look out at the night sky, seeing the cold brilliance of distant galaxies, we are not seeing objects suspended in emptiness. We are seeing the surface behavior of information arranged so precisely that it produces the illusion of depth. Space is not where things exist. Space is what information does. In a holographic universe, even time changes its meaning. We tend to imagine time as a river that flows from the past through the present into the future. But if space is not fundamental, then time may not be either. Time may be a record of how information changes. When entanglement patterns shift, we experience that shift as the passage of time. The future is not a destination waiting for us. It is a sequence of informational updates unfolding along the most probable path. Consider a simple atom. Its state evolves in tiny increments determined by quantum rules. Those rules are not written on spacetime. They define spacetime. The evolution of information gives rise to the sensation of time. In this sense, the universe does not move through time. Time is the bookkeeping of change inside the universe, just as gravity is the bookkeeping of entropy. Physicists search for a theory that unites the very large and the very small. They dream of a framework that explains both the smooth geometry of relativity and the jittering probability of quantum mechanics. For a long time, gravity resisted unification. It behaved differently, spoke a different language. Quantum mechanics was built from information. General relativity was built from geometry. The two refused to merge because they did not share a common foundation. The holographic principle offers that foundation. It shows that geometry is the shadow and information is the substance. When we stop trying to quantize gravity and instead understand how gravity emerges from quantum information, the conflict dissolves. The universe no longer contains two incompatible theories. It contains one informational framework expressed at different scales. At microscopic scales, entropy fluctuations are tiny. Entanglement rearranges constantly. Quantum mechanics rules. At large scales, entanglement accumulates and forms the smooth geometry we call spacetime. The curvature we identify as gravity appears. This means that gravity is not a bridge between quantum mechanics and relativity. Gravity is the bridge. Once this picture becomes clear, it changes how we think about existence itself. If the universe is fundamentally informational, then the laws of physics are not prescriptions written into the cosmos. They are the emergent behavior of statistics. They are the result of the most probable pattern. Reality is not commanded. Reality is permitted. In this view, the universe begins not with matter, but with information. Before particles, before stars, before even space-time, there are relationships. There is entanglement. As entanglement spreads, regions connect. As regions connect, space emerges. As space becomes continuous, curvature forms. As curvature forms, gravity appears. The world feels solid because we live inside the projection. We witness only the three-dimensional image, not the two-dimensional storage. Just as a hologram looks real from the right angle, the universe looks three-dimensional because the encoding is perfect. If the encoding had flaws, we would notice discontinuities in space. We do not. Space appears seamless because the informational network is seamless. One of the most striking implications of holography is that nothing inside a region of space is ever truly lost. Information may change form, but it persists. Even when matter falls into a black hole, the information that defined it remains stored on the surface of the horizon. The universe does not allow pure disappearance. Conservation of information may be more fundamental than conservation of energy. If everything is information, then the universe behaves like a computation. Not a computation in a machine made of metal and wires, but a natural computation woven into the fabric of existence. Each interaction updates the informational state. Each measurement selects a possible outcome from a probability field. Reality is the continual rewriting of the cosmic ledger. Looking at the night sky, it is tempting to feel small. Stars burn for billions of years. Galaxies rotate across distances beyond comprehension. Yet in an informational universe, smallness and largeness lose meaning. What matters is not mass or distance. What matters is connection. A single particle on Earth can share entanglement with a particle on the far side of the universe. That connection can be stronger than any spatial separation. We are not separate from the universe. We are woven into the same informational fabric. If the holographic principle is correct, then every moment of experience is the result of entanglement patterns shifting, updating, and generating the geometry we inhabit. You are not a being moving through space. You are a configuration of information participating in the construction of space. The more we search for what is fundamental, the more the universe whispers the same answer. Not matter, not energy, not even space-time. Information. And when we understand that, the universe stops appearing as a place. It becomes a process. There is a moment in every revolution when the familiar world begins to dissolve. For centuries, we pictured space as an empty container, a stage on which matter performs, a silent backdrop. But once physicists understood that space might emerge from entanglement, that picture began to crumble. Space is not a container. Space is a consequence. And gravity is not the sculptor of space. Gravity is the outcome of how space is stitched together. To grasp this, imagine removing entanglement from the universe. If two regions of space-time share no entanglement, no quantum connection links them. Without that connection, there is no shared geometry, no distance, no path. Space between them simply does not exist. The idea is unsettling because it means that the universe we walk through may not exist in the way our senses tell us. We feel distance as real. We feel separation as undeniable. But that feeling depends on entanglement, on invisible informational threads that connect one region to another. Without those threads, distance has no meaning. Mark van Raamsdonk offered a simple but powerful picture. He imagined two halves of a universe that are fully entangled. In that state, space-time forms a single, smooth, connected surface. Then, in his thought experiment, he reduced the entanglement little by little. At first, nothing dramatic happened, but as the entanglement continued to decrease, the geometry began to distort. The connection between the two regions weakened. Finally, when entanglement disappeared completely, space-time tore into two separate pieces. No bridge remained. The universe split not because of force, not because of motion, but because of a loss of information. In that picture, entanglement is not merely a property of quantum systems. Entanglement is the glue of the universe. Once that realization takes hold, even Einstein's curved space-time begins to look different. Instead of picturing mass pushing down on a rubber sheet, imagine that mass changes the entanglement structure of the informational network. When mass moves, it rearranges the pattern of connections. When the pattern shifts, space-time curves. The curvature is not fundamental. It is the visible shape of invisible entanglement. Gravity is not a command that matter obeys. Gravity is the result of space reshaping itself around information. To understand how deep this goes, imagine standing on a vast landscape that stretches out in every direction. You see hills and valleys. You assume the shape of the land is determined by the substance beneath your feet. But now imagine someone reveals that the land is not solid soil, but a woven fabric. The hills form where threads tighten. The valleys form where threads loosen. The terrain is not fundamental. The weave is fundamental. Once you understand that, you look down at the ground differently. You can imagine the hills rearranging if the weave changes. That is what physicists now feel when they look at space-time. They no longer see a solid stage. They see a weave of entanglement. One of the most surprising discoveries came when researchers realized that the amount of entanglement between two regions of space determines the area of the surface between them. That connection mirrors what Bekenstein discovered for black holes. Entropy lives not in the bulk, but on the boundary. The area of the horizon measures information. In ordinary space, the surface between two regions measures entanglement. One principle explains two very different phenomena. The overlap is not coincidence. It is evidence that these ideas are connected by the same underlying logic. The universe wastes nothing. When two independent insights lead to the same rule, nature is speaking clearly. If entanglement determines surfaces, then the geometry of space is not primordial. It is sculpted by information. And if information changes, geometry changes with it. That idea allows gravity to appear naturally, not as a force, but as a response. When mass enters a region, it changes the informational structure. The universe responds by adjusting geometry. Objects then move along the new geometry. We see motion, and we call it gravity. But the motion is simply matter flowing along the most probable path, a path allowed by the new entanglement configuration. It becomes impossible to describe gravity without describing information. Space is not empty distance. Space is a network of quantum relationships. Distance is the amount of missing entanglement. Gravity is the tendency of that network to seek equilibrium. These ideas do not require suspension of disbelief. They are grounded in mathematics and in results from quantum field theory and from the holographic principle. They have emerged not from speculation, but from the logical consequences of what black holes forced us to accept. Yet the most fascinating implication of this view is what it means for us. If everything in the universe is defined by information and relationships, then identity itself becomes relational. A particle is not a thing. It is an expression of entanglement. A star is not an isolated object. It is a central hub in an informational network. Even consciousness becomes part of that network. We are not separate from the universe that surrounds us. We are patterns within the same entangled fabric. When we look up at the night sky and trace the slow arch of the Milky Way, we are not observing objects held apart by empty space. We are seeing a stable arrangement of relationships held together by entanglement. The darkness between stars is not a void. It is the silent structure of information. Once this sinks in, the universe becomes more intimate. Space is not the distance between things. Space is the relationship between them. And we are part of that relationship. When physicists say that entanglement builds reality, they are not speaking metaphorically. They mean that without entanglement, there would be no geometry to hold anything together. A universe with no entanglement is a universe with no space. It is not empty, it is undefined. Entanglement gives the universe its shape. And the more entanglement there is, the smoother and more connected the geometry becomes. To see how this works, picture billions of quantum bits woven together. Each bit can be connected to any other bit through entanglement. When enough connections exist, a continuous space forms. That space behaves like the one described by Einstein, with curvature, distance, and gravitational effects. But if you begin cutting those connections, the smoothness dissolves. Distances grow, regions drift apart. At the limit, the fabric snaps. This is not speculation. It is derived from the mathematics of quantum field theory and from Maldaceno's demonstration that spacetime inside a volume can be fully described by information on its boundary. The more we study entanglement, the more it behaves like a force, not a concept. But unlike a force, entanglement does not push or pull. It shapes. It defines where motion can occur. The universe can be imagined as a map of relationships. Objects move not because they are forced to accelerate, but because the structure of entanglement guides them along the path of highest probability. When something happens that changes the entanglement network, space readjusts. We see curvature. We interpret that curvature as gravity. Even the flow of time becomes entanglement evolving. Time is not an external clock. Time is the decay or growth of quantum correlations. The past is a record of entanglement that no longer changes. The future is a field of possibilities waiting to be entangled. What we call the present is the moment where entanglement updates. We do not move through time. Time is the structure of how information changes. That is why quantum mechanics treats time so differently from space. Time is not a direction. Time is process. This perspective solves one of the most troubling paradoxes in physics, the conflict between quantum mechanics and general relativity. Quantum mechanics tells us that uncertainty rules. Particles exist in a haze of probabilities. General relativity insists that spacetime is smooth and continuous. These two pictures cannot be reconciled if space is fundamental. But if space is emergent, then the conflict disappears. Quantum mechanics does not need to obey spacetime. Spacetime must obey quantum mechanics. The probabilistic nature of the microscopic world shapes the geometry of the macroscopic world. When entanglement builds reality, gravity becomes the soft whisper of large-scale statistical behavior. It is not something the universe does. It is something the universe allows. Entropy always increases. Entanglement always updates. The geometry of spacetime always reflects those updates. Imagine watching two distant stars slowly circle one another. On the surface, it appears as a graceful dance guided by invisible force. But beneath that motion lies a constant rearranging of quantum relationships. Each change in entanglement shifts the geometry slightly. The path of the stars is the most probable sequence of changes that maximizes entropy. They are not following laws imposed from outside. They are following the architecture of information. The deeper implication is that nothing is isolated. Nothing exists alone. Even a single particle has meaning only through its relationships. A particle without entanglement is not somewhere in space. It has no location. It has no geometry. Only when it entangles with other systems does a place appear. The particle does not occupy space. The relationship defines space around it. This is why quantum mechanics always insists that measurement changes reality. When you observe a particle, you alter the entanglement pattern. You are not looking at something that was already fully formed. You are participating in its formation. Space itself shifts slightly as information updates. Observation and existence are no longer separate. They are part of the same informational process. The idea sounds strange until you consider the alternative. If space were fundamental, every location would need to exist independently of matter, energy, or information. But we have learned from black holes that information determines the shape of space. From Jacobson, we learned that Einstein's equations emerge from thermodynamics. From Verlinde, we learned that gravity emerges from entropy. And from Maldacena and Van Ramsdonk, we learned that entanglement builds spacetime. We are left with one inescapable conclusion. Geometry is not primary. Entanglement is primary. Once the universe is viewed this way, even the mystery of dark energy becomes less alien. If the expansion of space is not something happening inside spacetime, but something happening to the entanglement structure itself, then acceleration becomes the natural result of information spreading. As the universe grows, new regions become entangled. New entanglement produces new space. The expansion is not pushing galaxies apart, it is adding space between them. This is why distant galaxies are not moving away through pre-existing emptiness. The distance between them is increasing because the informational network is weaving new geometry. Space grows because entanglement grows. The universe expands, not because of outward motion, but because the fabric keeps building itself. At the most extreme scale, where entanglement fades and information thins, spacetime approaches its limits. Near the singularity of a black hole, entanglement patterns compress into a boundary. There, the holographic principle takes over. Space collapses into pure information. The interior becomes meaningless. Only the surface matters. Gravity has nothing left to shape because spacetime itself is gone. If space can break, if space can grow, if space can emerge from nothing more than information, then space is not a container. Space is a consequence. And when we finally let go of the myth of fundamental space, a new understanding emerges. We are not creatures moving through a pre-written universe. We are participants in the continual creation of space-time. Reality is not a place. It is a process of entanglement forever updating itself. The universe is not made of things. The universe is made of relations. Every bold theory eventually reaches the same unforgiving moment. The universe is asked to respond. If nature disagrees, the theory falls. If nature agrees, the world changes. This chapter is about that confrontation. If gravity emerges from entropy, then the universe should reveal it through measurable effects. Not poetry, not metaphor, evidence. The first test is simple to state but difficult to execute. If gravity comes from information, then regions of spacetime with more entanglement should exert more gravitational influence than regions with less. That sounds abstract, yet it leads to a clear prediction. On the scale of galaxies, where distances stretch into hundreds of thousands of light years, the informational structure of spacetime should add extra acceleration. This extra acceleration is what we interpreted for decades as the influence of dark matter. Dark matter was invented because gravity appeared stronger than it should be. Verlinde says the extra gravity comes not from hidden particles, but from hidden information. To test this requires more than star velocities. It requires weighing the gravitational field that surrounds entire galaxies. Nature offers a tool. When light passes near mass, spacetime curves and the path of that light bends. This bending is gravitational lensing. It reveals gravity without touching the object producing it. It is as if light acts as a messenger, reporting the curvature it experiences. In a universe dominated by ordinary matter plus dark matter, the lensing pattern should follow one shape. In a universe where gravity emerges from entropy, the lensing pattern should follow another. These signatures are different enough that telescopes can distinguish them. Researchers at the Leiden Observatory gathered data from tens of thousands of galaxies. They measured how the shapes of background galaxies distorted when viewed through foreground galaxies. Then they compared the lensing pattern with the prediction from emergent gravity. The match was not perfect, but it was far closer than anyone expected. Without inventing dark matter, without adding invisible mass, the entropic model generated the same gravitational behavior that dark matter was created to explain. It was not a coincidence. It was the first measurable sign that gravity might be emergent. But science does not crown a theory after one success. A theory must solve multiple puzzles, not just one. If entropic gravity is correct, then gravitational behavior in galaxy clusters should follow from informational structure as well. Galaxy clusters are immense gatherings of hundreds or thousands of galaxies. Their gravitational fields are stronger and more complex than those of a single galaxy. Dark matter explains that strength by adding mass. Emergent gravity must explain it by adding information. If the entanglement structure of spacetime increases with scale, then clusters should also show extra acceleration without needing invisible matter. Some analyses suggest that emergent gravity can match cluster behavior, but others indicate tension. Clusters remain one of the hardest tests. Dark matter fits them with ease because it adds mass. Emergent gravity must reproduce the same effect through entropy, which is more subtle. These difficulties do not disprove the theory, but they reveal where it must mature. A third test comes from the earliest light in the universe. The cosmic microwave background is a faint pattern left from when the universe was only about 380,000 years old. It is a map of tiny temperature differences across the early cosmos. Those differences eventually grew into galaxies and clusters. Dark matter influences how those patterns evolve. Without dark matter, the universe would not have formed structure fast enough. If emergent gravity is correct, its informational effects must influence the early universe in a way that replaces dark matter. Right now, the entropic model does not fully explain the early universe. It excels at describing galaxies today, but not the conditions that existed billions of years ago. It may be incomplete, or it may need a deeper connection to the holographic universe. A theory that claims information shapes gravity must be able to describe how information was distributed at the birth of spacetime. The fourth test arrives from a telescope that did not exist when Verlinde proposed his idea. The James Webb Space Telescope. Webb can see extremely distant galaxies. Galaxies formed when the universe was young. According to the traditional model, galaxies should take time to form and grow. But Webb has revealed massive galaxies far earlier than expected. They appear too quickly, too large, too developed. Dark matter struggles to explain this. If gravity emerges from information, and if entanglement drives structure formation, the universe could form galaxies faster. Entropy is efficient. Information spreads quickly. The early universe may have been a storm of entanglement instead of a slow process of gravitational collapse. Webb's discoveries are not yet understood fully. They do not prove emergent gravity, but they push cosmology into discomfort. When data challenges expectations, we must ask whether our assumptions are wrong. If dark matter were real, it should make early galaxies easier to form. Yet the galaxies Webb sees are even more developed than dark matter models predicted. The fifth test is philosophical only on the surface. A real theory must be falsifiable. If emergent gravity cannot be broken, it cannot be trusted. Verlinde has embraced this. He has written precise conditions under which his model fails. If gravitational lensing ever reveals mass that does not correspond to informational structure, the theory collapses. If we detect a dark matter particle directly, the entropic model loses its purpose. If black hole evaporation is found to erase information instead of storing it, the holographic foundation weakens. A theory must risk being wrong to deserve being right. The most profound consequence of these tests is that they force us to ask a deeper question. What is the universe made of? If emergent gravity continues to pass observational tests, then nature is telling us that space is not fundamental. Matter is not fundamental. Gravity is not fundamental. Information is fundamental. Entanglement becomes the architecture. Entropy becomes the rule. Geometry becomes the expression. Gravity becomes the echo. Science does not move forward by defending the familiar. It moves forward when evidence reveals that the familiar was only an approximation. If space emerges from entanglement, then every experiment that measures gravity is not testing motion. It is testing the structure of information. Some theories are beautiful. Some theories are elegant. Very few are testable. This one is. To understand how radical this shift is, consider what physicists have always assumed about forces. We believe that if something accelerates, a force must act. If a planet orbits, a gravitational pull must hold it. If a galaxy rotates faster than expected, there must be additional mass. This assumption shaped the entire concept of dark matter, but emergent gravity suggests something different. It suggests that motion may not require a cause in the traditional sense. Motion may be the natural consequence of information seeking equilibrium. When you pull on a rubber band, the resistance you feel is not a fundamental force. The rubber band pushes back because its molecules prefer a disordered state. Entropy drives the behavior. The tension is the result, not the cause. Verlinde says, gravity is that kind of result. Not a force, but a response. Not a command, but a consequence. Matter disturbs the informational structure of spacetime. Spacetime responds by reshaping itself. We witness the reshaping and call it gravity. The difference between these two descriptions is subtle but profound. One imagines gravity as something that acts on matter. The other imagines matter acting on information. If information changes, geometry changes. If geometry changes, motion adjusts. The universe becomes self-organizing, guided by probability rather than laws written into the void. Gravity is still predictable and calculable. What changes is the direction of explanation. Instead of starting with force and ending with motion, emergent gravity starts with information and ends with force. Testing the theory requires measuring information in a world where information is invisible. That is why gravitational lensing matters. Light does not lie. Light bends for every influence that shapes spacetime, whether caused by matter or by entropy. If information contributes to gravity, lensing must reveal that contribution. And it does. But tests must go further. They must be precise enough to show where the theory fails. They must be independent of assumptions about dark matter. They must be repeatable. Upcoming surveys will do exactly that. Instruments on Earth and satellites in space will map how space-time bends across billions of light years. They will measure not just galaxies, but filaments of the cosmic web. That web contains the largest structures the universe has ever built. If gravity emerges from information, these massive filaments should show entropic signatures. Their gravitational influence should not match the predictions of dark matter evenly. It should rise and fall with the informational density of spacetime. In addition to these surveys, scientists are building highly sensitive gravimeters, instruments capable of detecting tiny deviations from Newtonian predictions. If emergent gravity is correct, extremely small accelerations should behave differently from what Newton and Einstein predict. The edges of galaxies show this behavior. The question is whether we can measure it in controlled environments. Some teams hope to use precise satellite motion or laser interferometry to detect the faintest gravitational anomalies. If they succeed, emergent gravity will either gain strength or collapse. The stakes are enormous. If dark matter is eventually detected, emergent gravity will not simply be wrong, it will be unnecessary. If a particle is found, if a collision reveals even the faintest interaction, then dark matter becomes real. If that happens, the entropic framework will retreat to a supporting role. But if experiments continue to find nothing and gravitational behavior continues to match emergent models, then the universe will force us to accept a truth that once seemed unthinkable. Space and gravity may not be what we, believed. The final test comes not from telescopes or satellites, but from logic. The universe does not run two sets of rules. If space-time emerges from entanglement on one scale, then it must emerge on all scales. If gravity is entropic around galaxies, then it must be entropic everywhere. A theory cannot be partly emergent. Either space emerges, or it does not. Either information encodes geometry, or it does not. Either gravity results from entropy, or it does not. The most difficult test for any idea is simplicity. Does the theory reduce the number of assumptions? Does it remove unnecessary entities? Does it explain more by assuming less? Dark matter adds an entire new category of matter that no one has ever seen. Emergent gravity removes it. Dark matter needs unknown particles that interact only through gravity. Emergent gravity needs only information and entropy, two things we already know exist. When a theory explains more and assumes less, nature often favors it. Still, humility demands patience. Emergent gravity has not answered every question. It has not fully explained the early universe. It has not yet replaced dark matter in every simulation. But it has done something no alternative theory has managed for decades. It has offered a new path. It has shown that the mystery of missing mass might not be missing matter at all. It might be missing understanding about the nature of space-time. The universe does not care what we believe. It reveals itself only through evidence. Every observation either strengthens or weakens our ideas. One day, the data will decide. If emergent gravity falls, we will learn something. If it survives, we will learn something even greater. We will learn that gravity is not the foundation of reality. Reality is the foundation of gravity. We spent generations believing that gravity was the first truth of the universe. It pulled apples from branches. It shaped the orbits of planets. It forged stars and galaxies. It held the cosmos together. Every child learns that gravity is a force. Newton described it with a simple law. Einstein replaced the force with curved space-time. Across centuries, the story changed, yet our intuition stayed the same. Something out there pulls on everything else. Something reaches across emptiness and commands motion. We built science on that idea. But what if we mistook the shadow for the substance? What if gravity was never a force? What if we were watching the surface reflection of something deeper? The journey began with black holes. They forced us to admit that information matters. A black hole is not just mass and gravity. It is a thermodynamic object. It has entropy. It has temperature. The properties of that entropy scale not with volume, but with area. This strange relationship whispered that information lives on boundaries. It was our first clue that space behaves like a hologram. Then Jacobson showed that if space-time has entropy and temperature, Einstein's field equations emerge from the laws of thermodynamics. He did not assume gravity, he derived it. Then Verlinde took the final step. If gravity arises from entropy, then it is like the tension in a rubber band, not fundamental, emergent. When you stretch a rubber band, the molecules want to return to disorder. The band pulls inward because entropy prefers it. That pull feels like a force. It behaves like a force, but it is not one. It is a consequence. Verlinde suggested gravity works the same way. Matter disturbs the informational content of space-time. Entropy increases. The universe seeks balance. Matter moves along the path that restores that balance. We call the motion gravity. We observe the effect. We misinterpret the cause. If this idea is correct, then space is not a container. Space is a record. It is the bookkeeping of entanglement. The more entanglement exists between two regions of the universe, the more smoothly those regions connect. If entanglement decreases, connection weakens. If entanglement disappears, space tears. Van Ramsdonk showed that a universe can literally split apart when entanglement is removed. Space-time is stitched from relationships. When the stitching changes, geometry changes. Curvature bends. Objects move along new trajectories. We call those trajectories geodesics. We call that motion gravity. But what we are watching is the reshaping of the informational fabric. In this picture, you do not fall because gravity pulls. You fall because space-time relaxes. When you drop a stone, you are watching geometry adjust to entropy. When planets orbit a star, you are watching entanglement maintain equilibrium. The curvature is not caused by mass. The curvature expresses the informational response to mass. If space emerges, time must also emerge. Time is not a line that flows. Time is the constant updating of information. Every quantum event entangles systems and rewrites the configuration. The universe never moves through time. The universe changes its informational state. The feeling of the present is the act of entanglement. The past is the set of relationships that no longer change. The future is the set of possible relationships waiting to be formed. Time is not a river. Time is process. This new view does not weaken Einstein. It completes him. Einstein gave us the geometry. Entanglement gives us the reason for that geometry. Relativity described the stage. Quantum information builds the stage. The holographic principle revealed that the script is written on the boundary. Reality is not happening inside space. Space is the result of reality happening. Once we accept that space and time emerge, something astonishing follows. The universe is not made of matter or energy. It is made of information. Particles are stable patterns within the informational field. Forces are bookkeeping rules that describe how information can change. Even mass becomes a measure of information content. The energy in a system reflects how much information is required to describe it. The universe does not store mass. It stores information about mass. Look again at a galaxy. For decades, astronomers saw stars orbit too fast. They invented dark matter to fix the equations. They assumed more mass must be present. But emergent gravity suggests that the stars move that way because the space-time around them stores more information on large scales. At galactic distances, the entropic influence grows. Gravity strengthens not because more matter is present, but because information becomes dominant. The missing mass may not be missing matter. It may be missing understanding. Emergent gravity does not ask us to reject evidence. It asks us to reinterpret it. The universe was never obligated to match our assumptions. We assumed space was fundamental. We assumed forces were fundamental. We assumed matter was the basis of reality. Every assumption is now in question. Think of a hologram. The image looks solid. It looks three-dimensional. You could swear the object exists in depth. But the depth is illusion. The real information is stored on a flat surface. The universe may be the same. What we perceive as three-dimensional space may be an image encoded on a boundary beyond our perception. Our lives unfold inside the projection. We never see the surface. We see the result. If gravity is emergent, then we live inside a universe that constantly recalculates itself. Entropy increases, entanglement spreads, information restructures. The laws we experience are the statistical tendencies of this process. Everything stable is a balance of probabilities. Everything that moves is part of a search for equilibrium. Reality is not commanded by force. It is guided by inevitability. And what does that make us? We are not objects existing inside space. We are arrangements of information woven into the same fabric that builds space. When you look at the night sky, you are not gazing across emptiness. You are witnessing a vast informational network connecting stars, planets, and galaxies. You are part of that network. Your existence is not separate from the cosmos. Your consciousness is built from the same entanglement that holds space-time together. For centuries, we asked the wrong question. We asked what gravity is. The real question is why gravity appears. And now we know. Gravity appears because information demands it. Gravity is the language space-time uses to settle its accounting. It is the reflection of entropy acting on geometry. It is the memory of matter etched into the structure of the universe. Gravity is not the engine of the cosmos. It is the story the cosmos tells as it computes itself into existence. Reality is not held together by force. Reality is held together by information.